Okay, so, ladies and gentlemen, it's the final class. It was a heavy heart that I discussed that. And what this means at a practical level is putting a premium on triage, getting out a few extra topics and giving you a view of sort of where to go, where you might think about going from here, both in terms of modeling topics and in terms of cognate areas, other classes. So within the scope of today's class, what I wanted to do is to sort of very briefly go over a couple essentials on the best practices side, and then dive into a discussion of some modeling frontiers, which we haven't had time to talk about in class, but which are going to really shape modeling in years to come, and which are likely to sort of transform the importance of the skills you've learned within this class. But first I want to talk a little bit about best practices for modeling, because it's a very important consideration when building a model, and one that bears directly on the value delivered by that model. So really, as in software engineering, there's two very important concerns. We talk in software engineering about building the right program and building the program right. In software engineering, when we think about building the right program, what are we comparing against? What's our criteria for that? What's a primary importance when thinking about, have we built the right program, the right software system? I don't know how many of you are in 370, but if you're in 370, you should have encountered, begins with an R, ends with an S, and has a Q. Okay. I have a feeling there's going to be someone on the gallows soon. Okay, there's an R here. Okay. Requirements. Thank you. So requirements. Requirements. So with software engineering, we'll often work with a set of user-defined requirements up front, and then there's a set of derived requirements which are implied by those user-defined requirements, together with considerations of more technical nature, sort of what technologies are around, what sort of capacity they have, and in that add further requirements to the stack within which a program has to operate. And really, when we're dealing with software engineering, building the right program is about making sure we've got the right requirements, right in the sense that the user will be satisfied, not only because what they explicitly requested is true, but because it fits within the constraints of the technologies available, fits well to their needs within the context of those technologies. And similarly, for modeling, building the right model is about fitting in within constraints. It's not merely what the end user is looking for, it's what we can build with today's modeling packages within the time frame sought by the user, within the cost constraints, etc. And this has to do with the level of depth and breadth of the model, what's endogenous, exogenous, and ignored, those features which shape model boundaries. But what I'm going to talk about here in these couple of slides is building the model right, which is how do we actually go about building a model that's fit for purpose, which is suitable for delivering this right model? How do we make sure that our model isn't riddled with errors? How do we make sure that it's easy to evolve? How do we make sure that it's transparent so people throughout an interdisciplinary team can understand it? And broadly, to achieve that, just as in software engineering, there's a set of technical guidelines and a set of process guidelines. The process guidelines have to do with the procedures by which we build up this model, just as a similar set, have to do with procedures by which we build up a general program. And the technical guidelines have to do with the particulars of the technical choices made. And there's a bit of a gray area between them, but I've put up some guidelines here. And on the process side, I think some of the recommendations are most essential. So one of the absolutely central ones is to build this system up incrementally, step by step. Why do we do that? Why do we build a model up in a step-by-step incremental fashion? Just as, incidentally, as we do in an agile process for software. But with modeling, give me some of the advantages of doing that. Why not go for the big kahuna and just roll out, work assiduously towards having a model that has all the pieces in it, and having that be the first thing that's run, having that be the first thing that's put in front of stakeholders? Why build it up incrementally? Good. Catch bugs earlier is a lot of it. And that's a big motivation in software, right? But it's not only catching the bugs earlier. That's really important, because if we don't catch them earlier, we may go further down that track, build the top of them, and then we have a lot more rework to do. That is important. But it's not only discovering them earlier, it's being able to fix them quickly. Why do I say that? Well, if we find there's this distinction we make in software, and the same thing is true with modeling, but it's more tricky, between a fault and a failure. When we're testing a system, and we notice something is wrong, or we're using a model, or program for that matter, and we notice something is awry, something is off, no one's getting affected. No one's connected to anyone else. The model is frozen, it's not going anywhere. That's a failure that we're noticing. It's a gap between what we expected to see and what's actually visible. Now, in modeling of complex systems, this is more tricky, because sometimes there's a gap between what we expect to see and what we do see because of some failure of understanding on our part. Right? We're dealing with a complex system. System where emergent behavior contains surprises, almost by definition. So failures are almost to be expected as a result of failure of our mental model. But there are failures where the model is simply not behaving properly. And after some playing around, we may convince ourselves, yes, it's not behaving practically, or not behaving properly, or it may just require, maybe it's immediately apparent. But in order to go from that to the underlying fault that causes that failure, that's a process that we call what? In software engineering, what's this process for tracking down the underlying problem and fixing it? It's called, good. I was afraid I'd have to build another gallows. Debugging. Okay, so this is the debugging process. And if there's fewer things that have changed between iterations of our software, between steps of our software, if we've changed less since the last time we ran it, when this problem wasn't there, and now it is, we've changed fewer things, and therefore this bug is likely to live in fewer places. There's less things that we've added, for example. There's less things that could have gone wrong, between then and now, where things could have gone wrong. So if we move in small steps, we're more likely to catch those things. What's another motivation for this? So this is just develop incrementally. What's another motivation for developing incrementally? Well, if you go back to my slides back in September, you'll find a number of them. Number one is this ability to find bugs sooner. Another thing is to learn. You've added one thing into the model. If it doesn't have a problem, you can learn from it. You'll learn, adding that one thing caused this change. And that's really useful. To know where this certain behavior is coming from, for example. Often, if we have a big model just given to us, we don't know where the different patterns are coming from. what sort of led to what's essential for this pattern to appear. And if we're adding things incrementally in, it's more obvious. What's another reason for developing incrementally? We always have something in hand. We always have something that can deliver value. And we can pass it in front of a stakeholder. So, just as in agile approaches, where many of those concerns apply in the software development field, we secure a lot of benefit out of incremental development. But there's a set of other process guidelines that are also highly suggested. One of them is peer review. And for those who have taken 371, you will have undergone formal model inspections and have artifacts that you've created undergone peer desk checks, maybe pair programming, maybe in the form of circulating things for a walkthrough. But peer reviews are really, really important in software development. They're actually more effective, ladies and gentlemen, than testing both in terms of what bugs they can find and how efficiently, in terms of human time required per bug, they can find those bugs. Testing is absolutely essential for software development, but peer reviews are even a more powerful tool, particularly inspection, software inspections. And these same sort of peer reviews can be done for models. Can be done at many stages. In software development, what are some stages where we might do peer review, fruitfully? Can anyone say? Software development. What stages of software development, say for a given iteration of an agile process, or a whole version of software for a waterfall process, what are some stages where we might do peer review for software development? One is at the requirements phase. What's another phase that often occurs after requirements? Begins with a D, ends with an N, there's a G. Design, yeah. Design, okay. Design, okay. Another thing that we can review is often the code. Another thing would be the tests. Yes, thank you. The tests, okay, in software development, these are often key things to review. And so it is with models. But often, we have the scope of the model, what's in it, what's outside of it. That starts to delineate almost the requirements of the system. What are we going to build, not how. Elements of the model formulation and tests for the model. We haven't concentrated on tests in this class. But often when you build a model, you will have a few experiments, for example, that run the model under super simple conditions. Conditions where you think you should be able to anticipate what might happen. Maybe it's a one-person population. Maybe it's a case with a certain parameter set to 0. And you want to see how the model behaves for that. Okay? So testing is often very important here. Another thing that's critical in both software development and modeling is preserving multiple versions of a model. Why is version control? How many people in here have used Subversion? Good. Many of you in 2.14, right? How many have used Git? Okay, yeah. Good. So why use packages like that?
If somebody breaks something, you can break it to
Good. That's a big reason, Evan. So you'd like to be able to roll back to an earlier version, right? Big motivation. How about another motivation?
Allows multiple to work on it without having crossover files.
Excellent. So you can have multiple people contributing to the software without, in a fairly lightweight way, without the need to sort of each of them to have completely their own copies of all the files and to awkwardly integrate the others. Instead, it allows for sort of fine-grained updating of other people's and fairly easy testing against other people's contributions. And so it is with models, folks. You want to preserve modeling. But as we'll talk about, Turns out models at this point, you think about any logic, it's pretty poor at allowing separate development of pieces of the model. That's an area of growth for that product and for most models, in fact. Another really strong process guideline is keeping track of experiments. You may have seen this even in your problem sets. Sometimes running a model, you want to be very careful what you're running it with, what did you see as an outcome, and particularly if you're dealing with a quite big model, keeping track of successive experiments with the model is really important to be clear about what you've learned from that model. Another thing was this whole idea of continuous integration. It kind of goes along with version control. Integrating with others' work frequently and in small steps. And this also has lots of motivations for it, but basically you're less likely to run directly in conflict with someone else's work if you're integrating it over time. You're less likely to duplicate large portions of their work. You're updating over time for their work, and if your systems are incompatible, you'll know it sooner rather than later. You know, one of the old problems that used to be a giant issue in software development, and it's still a substantive issue, is issues having to do with where you have a team, and the integration of the team's work occurs late in the game, in the so-called Big Bang. Big Bang because things blow up. It doesn't fit together. Have you ever had that happen with your team? You've gone off and created component A, someone else has gone off and created component B, and both of them may be really good. Both may be perfectly reasonable, but they've made the wrong assumptions about how they fit together with the others, and you put them together and it just don't work. Have you ever had that experience? It doesn't line up. Maybe you discover you've duplicated some code. That's a less bad situation. What's worse is no one did a certain thing, or even worse, there's this subtle incompatibility. You did things expecting this, they did things expecting that, and it doesn't jive, it doesn't fit together. So with modeling too, if you have different people working on different areas of your model, you want them to make those contributions not on the basis of months of work that finally have to be brought together, but just a day of work at a time, and integrating frequently. And this is critical. Ladies and gentlemen, many of you may forswear modeling after this class. You're not interested in simulation. You may end up coming back to it because it's going to be becoming more and more ubiquitous in terms of where you see it popping up. But even if you don't aspire to being involved in the simulation as a technique, one of the most important things you can do as a software developer is to use discovery of failures and their underlying faults to identify problems not only in the program but in the process. What is it that allowed this problem to be discovered only late in the game? What is it that allowed it to elude our efforts to discover it sooner? What is it that made me miss it for so long? What is it that led it to be incorporated into the model in the first place, or into the program in the first place? This is really important. It's not about just debugging the program, ladies and gentlemen. You should be debugging your development processes, your model development processes or your software development processes, trying to learn from mistakes. And this is a broader principle in mind. If we make mistakes, we sometimes think of mistakes as a failure. We think of mistakes as something to be ashamed about. But a mistake can be an asset if you can learn from it effectively. If you can honestly take a look at that mistake, say, yes, there was a mistake, what can I do to avoid similar mistakes in the future? You can actually get a net gain from that mistake. You can actually turn it around and invest in your software development process or invest in your learning process so that mistake doesn't come up again. So using discovery of bugs in model, discovery of bugs in program to improve the underlying process. Maybe it's your testing. Maybe it's your documentation. Maybe it's your requirements. Maybe it's aspects of how you design a system and communicate that design. But if you can use the bugs to discover problems in your process, you can often get far ahead from where you would have been had that bug not been discovered. So this is some process guidelines, and I've supplemented them with some others here that sort of restate some of the same things, and I think may have one or two additional items as well. Okay, in terms of technical guidelines, technical sort of tips here. A number of things that can be done. Many of you have been pretty happy with the attendance of office hours through the term and recently as well. And many of you have had the experience of sitting down with me with a model and having me help you try to identify problems with it. And that's a good experience to have. It's a good experience to have. In CMPT 470 next term, we're going to be talking quite a bit about model debugging. And there is an order of magnitude difference, at least, between how quickly people debug a given problem. And it's not because of how smart people are purely. A lot of it is the process they go through. But also the particular techniques they use to advance that process. And many of you have, for example, had this experience of having me do a bit of logging. I stick in a trace ln statement, trace line, and I'll print something out within this. Often it's a very simple thing. Numbers on one, numbers on two. Just to indicate it's getting to a certain place, that something is happening, or look for its absence, it's not happening. And in general, that can be generalized to configurable logging. So again, if you folks are in 470, you'll learn some about Java 8's logging library and its use of lambda expressions to do it in a lightweight way. But ladies and gentlemen, if you're not familiar with Java 8 or you're not familiar with Java logging utilities like log4j, you might want to be. These are extremely useful tools to understand what's going on in a program, what's going on in a model, and basically allow you to declaratively, without recompiling your application, without going and rebuilding, you can declaratively specify in a config file, what information you want it to log, what depth of information, how much information about what's going on. Configurable logging tools are really valuable to keep track of what's happening within a program. And they can be used very well with models also. So logging is one of those tools that can be really useful for not just debugging, but understanding performance constraints, understanding challenges having to do with the operation of high-level components of the system, understanding the system. Complexity. Much of modeling is an attempt to simplify things. And there's some things we haven't talked about, but I've mentioned to some of you. In fact, just earlier today, I was mentioning one of AnyLogic's capabilities that simplifies a model, for example, with inheritance. AnyLogic does support inheritance of one agent from another. You can define a person agent and perhaps a patient and a doctor, for example. And they both inherit from, they're both subclasses of person. And so rather than putting the same mechanisms in both patient and doctor just by cut and paste, you can place it in person. And by placing it in person, both can inherit it. It only has to be modified one place, only has to be fixed one place. And it's less likely to yield bugs. More than that, with state charts or with events and how we keep track of things, keeping track of things with greater clarity, simpler, fewer moving pieces, moving parts is often to our advantage. And with models, a lot of the trick has to do with setting this boundary between endogenous, exogenous, and ignored. That's not what I wanted. This model boundary between these three here, having to do with model scope. There's a principle in software development that we talk about, particularly in the agile development area, which applies to modeling. Perhaps some of you have seen it before. It's called the Agni Principle. Y-A-G-N-I. And it goes along with incremental software development. It goes along with incremental model, building a model in pieces. Does anyone know what this stands for? Maybe I need an inverse game of hangman here. Maybe we'll unhang the person on the gallows or something like that. Okay, we're removing his legs now. What is the Y? Yeah. Okay. Great. You won the game. Thank you, Alex. You ain't gonna need it. And basically, it's about not trying to stuff unneeded functionality, unneeded pieces into a piece of software for a given iteration. We software developers, particularly, are sometimes an ornery lot. We want to put extra features in we think will be cool, will be neat to implement, will be showing the sophistication or the flexibility of our system. Agni is basically saying, don't put in things that you're not sure are needed. If you're not sure the client's going to need it, don't put it in yet. And if they request it later, then you can put it in. And you do so in incremental deliveries of the system. And so it is, ladies and gentlemen, with models. One of the biggest things that can slow down a model project is you put all sorts of stuff in the endogenous side that's not needed. You put all sorts of extra features into the model, which you're not going to use. Now, why does it matter? I mean, what's the matter with putting extra stuff into a program? What's the matter of putting extra stuff into a model? Why is that bad? After all, isn't that adding flexibility? Isn't it adding a generality? Isn't it making a sort of more sophisticated model? Why is it bad? What are the problems there? The problem is one of what? I'm going to throw out this term. It's a very important term in software development to keep in mind, and it's a very important term from a systems thinking perspective. And it has to do with the opportunity cost. What is opportunity cost? Can anyone say? When we talk about the opportunity cost of an investment, opportunity cost of a given sort of line of work, what are we talking about? What are we considering? It's the cost of the choice. Because making that choice, ladies and gentlemen, often forgoes value from other directions. So this is mark my words. Mark my words. This is the value of options foregone. Okay. In other words, they say in Latin, the word decide means to cut a branch. You make one choice, and that choice may have value, but by making that choice, you have foregone, you have sacrificed, you have cut off other options. So by putting all this effort into this generality, putting lots of things in endogenously in the modeling, that's taken time away from something else. And in software development, putting all this extra features into one thing is inevitably taking our time away from something else. Maybe it's from testing. Maybe it's from being able to bring back to the user and getting even clearer on certain other requirements. It basically is it's subtracting value from opportunities that we haven't been able to undertake. So the Agni Principles is a nod to that. It's saying, don't put these things in, because there may be even more valuable things you can put in. It's not these things that you put in are worthless, often far from it. It's just that by putting them in, we've ruled out other investments. Does that make sense? Opportunity costs, ladies and gentlemen. Opportunity costs are first and foremost in front of us during software development. Software development is in so many ways, and model development too, is in so many ways a risk management exercise. We can't exhaustively test our program. We can't perfectly peer review it. We have to take the limited time that we have and put it to best effects, invest it to best effects. And so it is with modeling. We have limited time to build up this model. We don't have the option of building a perfect model of the world. Instead, we have to make do with the limited time that we have to yield the model be robust and effective within the scope of that time. So what we put in is very important. And foregoing things, you ain't gonna need it. In other words, holding off on putting something in until you're absolutely sure that it is going to be required, that it's a priority. We'll save that time for something else. So, before you gold plate something, before you gild the lily, you take something that's beautiful already and you paint gold all over it. You have to consider, what am I sacrificing by doing this? It's an aspect of systems thinking beyond the particular choice that you're making to the choices you're not making, and what things you're sacrificing with them. Ladies and gentlemen, abstraction encapsulation. I talked in this room last time and the time before about metalinguistic abstraction, using the right modeling language, the right primitive, the right basis set, the right sort of pieces, set of pieces for one task as opposed to another task. And much of modeling is about building abstractions. Much of computer science, ladies and gentlemen, is about building abstractions. It's about building these pieces of a program that hide a lot of the details, expose contracts, expose elements that guarantee what, but hide the how. They hide a lot of details, so that you can use those in flexible and useful ways. And so within modeling, a lot of what we do is actually building up elements, whether it's state charts or functions, that will hide unnecessary details, because unnecessary details overwhelm us with complexity. Name things very carefully. I have erred in this class on the side of longer names. You no doubt have noticed, right? The point is to choose intentionally selected names that communicate effectively. And it's not so much a matter of one convention is the best, but it's a matter of within a given team having a clear convention by which you can communicate clearly across that team. Okay? Designing code for transparency and modifiability, for flexibility. Flexibility, ladies and gentlemen, has value. If you go over at Edward School of Business, they'll talk about real options, for example. Flexibility has value. The ability to sort of quickly address a new emergent need is really valuable. The stakeholder says, you know, this great opportunity has come up. I need the model by next week to have this feature in it. Or you're working on a software development project and an amazing possible client comes about, and for it to be responsive to their needs, they need these features put in it quickly. Flexibility has great value there. Transparency as well. You can have many people come to your model, many people come to your program, and they'll understand it quickly, can come up to speed, start contributing to it. Very important for models, important for software development in general. Naming things carefully can allow sometimes a more or less self-documenting model, where people can look it over and understand a lot of the pieces from the names. You know, in software development, we talk about defensive programming, putting in place checks to make sure that certain conditions, for example, are handled, or put in place things that are going to for example, check if a null value has been received, check if the model population size is 0, and handle that, etc. So defensive programming, and I also talk in 470 or 371 about offensive programming. Actually going out deliberately and trying to find problems within the program. Going out and actually putting in place mechanisms that will proactively discover issues within a program. Those who took 214 from me some years ago may remember this idea of, for example, putting in place special values in the heap so that when you read out of a pointer, an error will occur if it's reading some amount of memory that it shouldn't be, some area of memory it shouldn't be. Defensive programming and offensive programming are topics that I touch on in 371, also with the use of what are called assertions. And we haven't talked about that in this class. What's an assertion, ladies and gentlemen? It's a very important technique of defensive programming. And it's an extremely practical one. If you go out into industry and you're working with a lot of different languages, assertions will be one of the tools they use to find problems. Tell me what an assertion is.
Basically a statement that'll crash the program if it fails.
Good. Excellent, Evan. So it's a conditional, so an if statement, for example, that will check some criteria. And that criteria is basically asking, are things sane? In other words, are my assumptions, the programmer's assumptions, the developer's assumptions, are those indeed the case? Are they indeed solid? Are they indeed correct? Are my assumptions borne out? If not, bomb out of here. Now that may sound perverse. Why would you want to bomb out of there? Well, if you're in the middle of testing, you want it to alert you as soon as possible to a problem. And so testing the assumptions of the programmer and flagging if they are not, in fact, correct, if they're not, in fact, true, is a very important part of finding bugs in the program, finding bugs in a model. So proactively putting in assertions for your assumptions when you build up code is very valuable. And when you build up a model, putting in assertion statements, asserts in Java, there's actually a statement to do this. Have you seen that before? It's a keyword in Java. Assert. How many people have used assertions before? Okay, I don't have to talk a lot about it, but basically, you assert some predicate, right? You assert this thing is non-null, or you assert that the population has at least a certain number of people in it. You assert that this given person is in the population, whatever it is. You assert some claim, and it'll check that at runtime. Now, often these things are disabled when you're running the model for a stakeholder, when you're outside of the development or testing loop. But sometimes they're left in there as well, even in that phase. There's different philosophies with respect to it. But sometimes these assertions can be quite sophisticated. For example, check if this brute force algorithm gives the same result as this very clever algorithm that could have some missed cases. You're not completely certain of its correctness. You test it, you compare the results for that brute force algorithm against this clever algorithm, make sure during testing that they always match up. And then finally, using type checking to advantage. We did that in our modeling using things like option lists to encode values. We could have encoded values for messages with strings. We could have encoded them with numbers. Why use options lists? We could have encoded sex with a 1 and 0. We could have included someone's province with from 0 to 14 or 0 to 13. Why wouldn't we do that? Province or territory. Why wouldn't we do that? It's more descriptive is one of the things. So an option list is more descriptive. It's more transparent. So that's one of the things. You can look at it and see what it is. But what's another reason?
Type checking will alert you to mistakes.
Yes, type checking. The compiler is your friend. I know some of you have had a love-hate relationship probably with builds and compilers. Sometimes the compiler didn't seem a friend, right? that midnight time over in S320 when you're back in your first year, and it was just spitting mad and throwing out errors. Actually, it was your friend. Good friends, ladies and gentlemen, a true trusted friend can tell you things you don't want to hear, but you need to. And so it is with builds, so it is with compilers. Type checking, ladies and gentlemen, is one of the things a compiler will do, a build system will do, that will alert you to problems that you otherwise didn't realize. And we can use that to our advantage through options lists. This will prevent us from assigning a sex to a province, because both are encoded as 2 or 1. And type checking in general can be used to spot issues with your program more quickly if we can take advantage of it. And option lists, in short, enums, which is what they turn into, are one of the best ways to do this. So ladies and gentlemen, I have many other material here. You may not have known that AnyLogic can generate documentation on models. What's output, it can generate information on what's output. I have slides on incremental delivery, peer reviews, and all sorts of other good things. But ladies and gentlemen, this would offer value, but there's an opportunity cost for presenting it, because I would not be able to present something else. So I want to present something else, and I will go to that now. But with this, I will post these slides so that you can see further expounding on some aspects. So next, I'd like to talk about some dynamic modeling frontiers. These are frontiers that are going to transform the practice of modeling in coming years. There's a number that I could put up here. Many of them have to do with changes in science more generally. For example, the emergence of what's sometimes known as big data or data science, the emergence of large amounts of electronically sourced information about the world. Maybe it's environmental sensors, maybe it's data from sensors on our smartphones, maybe it's information from point of sale data when you purchase something. This sort of data offers huge potential for informing models, and in fact, it's transforming large areas of science in general. Others of these modeling frontiers reflect changes in software development or computer science. For example, the ability to tap modern software engineering practices, ability to tap, for example, improvements in languages. The languages we use for building programs can be applied for modeling. I'm going to just touch on a few of these in the time that remains before we wrap up with some additional concluding comments on the class level. So one of the topics you got a glimpse of, my student Kurt Kruger talked about multi-scale and hybrid modeling, the fact that multiple system science methodologies are really highly complementary. Maybe someone could open that door over there. Oh, no, sorry, I thought Ansgar was trying to get in, he was trying to escape. Okay, I sympathize. So multiple system science methodologies are actually quite complementary. They're often seen as alternatives, but often they can be woven together so the whole is greater than the sum of the parts, so that you can have a model where different pieces of the model are a good fit to that area of the problem. And multi-framework modeling is, I think, going to be the norm here. And you're some of the few people in the world that have gotten exposed in a class to multi-framework modeling. You may not be patting yourself on your back, but perhaps you should be, in the sense that there's a lot of need for people who understand not just one technique, but multiple techniques and how they can be used together. It's extremely rare to find people with that understanding of how they can fit together. I want to talk about this issue of integration with big data. So, a lot of the time we're building these simulation models that are quite rich and that capture information that it's hard to get reliable understanding of from public sources, from papers published, etc. If you're working in the health area, there's a lot of aspects of health behavior. Things like people's location, physical activity that they undertake, their proximity to each other, their social context, who's around them, and what they're engaged in terms of communication and their decision-making strategies. These are very hard things to gain information about through traditional means. It turns out that people have done studies looking at physical activity, comparing what people say versus what's indicated via these things called accelerometers, these things that keep track of their physical activity and measure it physically. And it's like a world apart. What people say their weight is versus their actual weight, big discrepancies. Big discrepancies in terms of what people say they eat versus how they actually eat, etc. So a lot of these things are hard to get information about. And absent that information, the ability to use models to evaluate at a quantitative level trade-offs between policies is hard. Now, fortunately, we're living in a world where a lot of tools that can help give us insight are now becoming commonplace. And they're becoming commonplace in the form of consumer electronic devices like smartphones. So, it's widely known. I mean, I think everyone in this class probably been struck at one point or another by how much value you can get from a smartphone, the functionality involved. What's less widely appreciated, probably many of you do realize this, but a lot of people don't, is that a lot of this functionality is due to things that are sensors at one level or another. Things like accelerometers. Where's the accelerometer used in your phone? Anyone know? If I pull out my Android phone here. Why would this device have an accelerometer associated with it? Sorry?
Rotating your phone.
Yeah, it's for rotating the phone. It's actually a very sophisticated accelerometer, but it's basically used at an operational level to do the screen rotation properly. So I can look at it, I can read a document this way or this one. Quite useful, but it can be used for a lot more than that. There are sensors in the form of microphones and cameras, right? There are sensors in the form of GPS to know where we are. In fact, there are sensors for things like Wi-Fi that are used, again, very operationally to figure out where the nearest Wi-Fi router is of a given sort and communicate with that one. And there are sensors used for things like managing the battery temperature, slowing down the processor if the battery's getting too hot, etc. Now, these sensors can be repurposed at little or no cost for sensing, actually, for knowing what's around us. So we, for example, in our work, have for about 6 years now been working with smartphone-based technologies to collect information from a wide variety of sensors. These are just a few of them there. And to integrate that with data reported by people via buttons or asked in questions. So this is just one system. There's other systems out there. Ours happens to be probably the most sophisticated system in the world for doing this. But a lot of what I'm going to be telling you about is how the data from these systems can be used together with models. Increasingly, these systems are packaged together with consumer electronics. In our case, it's a distributed system, so you have on-smartphone app, which sends data up to servers, which can then process it, including with tools like agent-based simulation, tools like AnyLogic, that can be used for simulating scenarios that have been parameterized by data from the smartphone. Think about, for example, having a network in your AnyLogic model where instead of AnyLogic creating that network, it actually reads it in from a database or reads it in real time from data collected via phones, for example. So you can actually get data from the world which will end up being flowing into, say, your AnyLogic model to allow some simulations. So we can keep track of, for example, people's movements over time, people who live in different areas of the city, what sort of things they're exposed to. We can figure out where people are indoors through Wi-Fi signal strength. We can look at contact patterns and how they change, not only week to week here, but also in terms of minute to minute. And we can look at things like how long people are in contact with each other to get an understanding of sort of the patterns that might govern spread of pathogen or spread of ideas, etc. Now, in our particular device, we complement this, our particular app, we complement this with questionnaire information, all of which can be specified typically without any programming, just in JSON files, for example. And these things can be triggered based on certain contexts with a little bit more sophistication. and also with buttons that can be used to proactively report things. So, for example, I've taken some medicine, or I've just eaten, or I'm going swimming in a slough, or what have you. Now, what does all of this have to do with dynamic models? Well, it turns out that the data from these sort of systems is of great value for the dynamic models. The models often are really thirsty for information, thirsty for data, thirsty for evidence. And the type of information that can be picked up on smartphones, oh my gosh, before it breaks. The data that can be picked up on smartphones like these can be really useful for filling in some gaps here, really useful for understanding some of the patterns of behavior that might be posited, might be theorized about within the context of dynamic models. And models, in turn, can help make sense of all this data, this cacophony of data that's coming in from environmental sensors, from weather information, from smartphones, from point-of-sale data, from social media feeds, etc. You can make sense of a lot of it using dynamic models as a lens to sort of explain and help understand the implications of this data. I don't have time to go into lots of details of this, but suffice it to say that this is an almost ideal marriage, because the dynamic models help take this data and link it up with choices to be made. If I do this, if I do that, what's the implications? And the big data can help fill in the gaps in these models. So, we've combined this sort of data with models by parameterizing the models, using, for example, putting in mobility patterns into the models that are measured from smartphones, or putting in contact patterns, directly putting them into the model. Alternatively, you may calibrate a model to this sort of data. Remember, with calibration, we're dealing with emergent patterns from the model. You can't directly put those patterns into the model. They emerge from the model, but we can compare those emergent patterns with what we observe from this big data. We can do inferencing based on this data. For example, trying to identify how the bug is spreading within a long-term care facility, within a nursing home. We can train a model on the data. For example, we can try to use the model to classify, and we can use data as a sort of ground truth to evaluate inferencing schemes. So we can use data, for example, from a simulation model to judge possible classification schemes. So that was one aspect of sort of the emergence of big data. A couple more components. One thing related to this is this emergence in what's called now increasingly data science, linking up basically dynamic simulation with computational statistics. Now, this is probably not an area that you folks have been exposed to as undergrads, but it's an area which, once again, in the big data context, is becoming increasingly important. And that is, as one former professor of mine put it, so I had a professor back before you folks were born, I think it was 1990, and he was an expert in statistics. And I went and I heard a talk by him about 2 years ago. He's a professor now at Berkeley, UC Berkeley, and he basically said computer science and statistics are as fields on a collision course, not in the sense that they're going to conflict, but in the sense that they're merging together. Increasingly, statisticians have to think like computer scientists, and computer scientists need to think about issues that statisticians deal with day to day, about the value of data. Viewing data. So a lot of you folks have taken 360, I think, algorithms. Is that right? Most of you folks? So in algorithms, you probably talked a lot about time complexity of algorithms. Is that right? O of n squared, O of n cubed, exponential time algorithm. Is that right? Yeah? Yeah. So did you also talk about space complexity? How much space an algorithm would need to do its job? Mm-hmm. Yeah? Yeah, okay. So that's the traditional view of computer science. space is a necessary evil. You know, for this algorithm to do its job, we need a certain amount of space. And that's fine. But increasingly, ladies and gentlemen, that space is occupied by data that has value. It can help the algorithm work more effectively. Instead of treating the space as filled up as just a burden, something to be worked around, we can actually view it as an opportunity to improve the algorithm performance. We can use it for smarts of the algorithm, because increasingly we're working with data which can actually inform how the algorithm could behave more effectively. So here's arguing computer science and statistics in many ways are merging. And there's this emerging field of computational statistics, which it turns out can be used very well with dynamic simulation. And just to give you a sense of what's going on here, ladies and gentlemen, there's this opportunity to build what I like to call closed loop models. The idea here is that we take a model, maybe it's a rough and ready model, a model we have to build really quickly because of some emergent condition. You know, you folks probably barely remember swine flu. Remember swine flu? Yeah, okay. And you know, there's a bunch of other diseases like that. In the past year or so, there's been MERS, Middle Eastern Respiratory Syndrome. Back when you folks were, well, you weren't still in diapers, but you were younger, for sure. Maybe you were in diapers, some of you. I don't know. I won't dwell on that. But there was SARS. Does anyone remember SARS? Yeah, okay. So SARS was this bug that emerged from Asia, and actually it killed a large number of people in Hong Kong, areas of China, Toronto, and Singapore. I was actually, at that time, I was a consultant. I was flying back and forth through Singapore, and I had folks, you know, imaging me with infrared. Excuse me, it was infrared, far infrared imagers. You know, me with all other people getting off the plane that you had to report if you had coughs or what have you. And you think about a bug like that, there's not a lot of time to build a model about it, to help give advice. And often, the models that we build, there's not a lot of great data to tie down many aspects of the model. You're kind of working in a data shortage because a lot of aspects of the bug haven't been studied well yet. So you can build a model, but you're not sure how good the model is. But meanwhile, there's data coming in over time. There's data coming in that is cluing you in to the patterns that are being seen. And these techniques, these predictor-corrector methods, the primary one of which is shown here, is called a particle filter, can basically bring together the model on the one hand and the incoming data on the other. And the idea, ladies and gentlemen, is that the model learns over time from the data. So rather than just taking a model, building it and putting faith in it and using it to give advice, what you instead have is a model set up so that you can use it at any time to do projections forward, to ask what if we did this, what if we do that. But over time, the model's understanding of what the current situation is and what values of parameters are being modified as the data comes in. It's almost like it's being dynamically recalibrated to take into account the latest data. And I've shown here an example of an extremely crude model, one that was knowingly very far off from what the data would suggest. And you see this model is kind of projecting forward, not just one value, but a whole distribution of values. And it's projecting forward in the absence of data for a while, and then suddenly some new data comes in, and it sort of regrounds the model. It says, whoa, hold your horses. You know, this data is much slower than you thought, and the model says, oh, okay, you know, I better adjust my understanding, and then projects forward from here. Now, in this case, it isn't even learning nearly as much as it could about the value of parameters, which is another whole sort of use of this technique, which really brings in extra learning. But the point is, this technique, as new data comes in, as shown as these kind of dots here, it's correcting model projections, and it's helping the model to learn from that new data to update its estimates of parameters and the current situation, the current state of the model. So here we have fallible model predictions, a model that could be really off base in certain regards, but probably captures a lot of the structural elements of what's going on out there in the population. So still really good for looking forward at some level. It's just that it's off in certain regards. And then you have noisy data. Data, ladies and gentlemen, is not from heaven. Data often is full of problems of its own. But you take imperfect data, imperfect models, and it turns out that these computational statistic techniques can combine together them to get the best of both. So you can have a model that can look forward, can ask about counterfactuals, ask about interventions, for example, and you have data which is keeping the model honest, which is keeping on regrounding the model. So these are these so-called predictor-corrector methods, and what I've shown there is what's called particle filtering. It's a sequential Monte Carlo method, and it's one that we're really excited about because it can be used with a wide range of computational models and can be used with incoming data streams of all different sorts in a very general sort of way. So you think about the big data that I'm talking about, from smartphones, big data from environmental sensors, pollutant sensors in large cities or what have you. You feed it into a model, you can do a lot in a live basis with that model. Again, it's no longer about taking that model, putting trust in it. It's about keeping that model always kept honest by new data. And there's a technique called the Kalman filter, which is somewhat similar, though more restricted. Okay, I don't have time to go into this. Some other techniques known as MCMC, which allow us to kind of, instead of getting out of calibration, we got single values when we ran it, right? For your problem set 4, you were trying to estimate the best value of parameters so that it could best match the data, right? Those 2 time series of data. By the way, if you haven't started problem set 4, it'd be good idea to do so. But the other thing is, take a look at the data I've provided you. It uses data specified in months, like 0.06, 0.09, 0.03, and those are every few days and months terms. Take a look at that. It may help you understand some things. But what comes out of that calibration, ladies and gentlemen, are point estimates. Estimates of the best value of a parameter. But it doesn't give you a sense of the uncertainty involved. And these MCMC methods can do exactly that. They could say, well, this parameter is in this range, this parameter is in this range. This is the highest likelihood area, but if this parameter is higher, it means this one also needs to be higher. And you can delineate these probability distributions associated with the parameters. So instead of getting point estimates, a single estimate for each value, you can get probability distributions out. And then you can use these probability distributions, draw from them to get outputs from the model that are in probability distributions as well. Just a few more things here before we wrap up. One thing is, ladies and gentlemen, model specifications and domain-specific languages. Okay, system dynamics, the tool that we started with. It's perhaps most notable of all these techniques we've been using because it has this declarative model specification. We specify what we want to obtain as relationships between stocks and flows. We specify we want this flow to be given by this formula. We want this stock to have these flows into it and these flows out of it. And we don't really have to go much into the how. We don't have to go into loop over this and call off to that, and if this is the case. It takes care of a lot of details of that. By contrast, ABMs, agent-based models, make use of general-purpose programming languages. And there's much promise for improving languages in the ABM front. And one of the areas that I'm working with another professor, probably some of you have taken, are some people on 370 right now? Yeah, Professor Duchin. Yeah. So he and I are working on languages for agent-based modeling that will be more declarative. You specify what you want to obtain, and you don't have to go into all the gory details as much about the how. Does anyone recognize this language? Anyone? Does it look a little bit like a language you've seen before? Yeah, I should pass out the notes for this and that, right? Anyone recognize?
Is it Python?
It's actually not Python, though it has a minimalist syntax that you might think is kind of Python-like. Well, it's actually based on something very close to Haskell. How many people have seen Haskell? Yeah, okay. Haskell is a functional programming language, much like Lisp, Scheme. I think Bernd was telling me, I think there's Racket now. Racket's a version of Scheme. It's PLT Scheme renamed. I found that out. Oh man. They just changed the name of it. Okay, it used to be called PLT Scheme. But basically, it's a modeling it's a language, Haskell, and this group of languages that allow for a very mathematical style of programming. You can substitute in the formula for something for uses of variables, and it supports what's called equational reasoning, in the same sense used with mathematics. And it tends to be quite declarative in terms of allowing you to specify what you want and less on the how. Another area that we're working on is this area of collaborative modeling. So helping to enable modeling collaboration that goes beyond what current systems can offer. So most of the models that we built in class here have been built by you individually. Some people are working in teams. And this is a little bit of a gap from what you see out there in the world, where most modeling that's ambitious gets undertaken in interdisciplinary teams. And the actual model is a way of helping the team communicate with each other in many cases. And having involvement in that model across the team is really, really important for model correctness, for bringing people able to sort of say, this is wrong in the model, to help inform the values of parameters used in the model, to get a sense of ownership by people such as clients with the model. It's really important for them to be able to look at the model. And current modeling packages provide quite poor support, and I'd include in here most emphatically AnyLogic. Particularly folks, ladies and gentlemen, of your generation. Your generation, I think, is more so than any that's preceded it, used to being able to collaborate online in an immersive fashion. And I don't care whether it's Google Docs or large-scale games. You expect to be able to, in a seamless way, interact with others online. And unfortunately, the type of packages we see with AnyLogic, the desktop software, is not very supportive of that collaborative work. You know, tools like Git have brought us able to work more collaboratively when it comes to software development, but modeling is lacking at this point. And I think there's greatly enhanced potential for modeling projects if there are ways that diverse modeling team members can, for example, perform model mapping, map out what might be in a model, what might be left out, create and modify elements of the model. So in other words, if you could actually build up what's in the canvas of AnyLogic online with a set of others at the same time, or modify those things. If you could add scenarios in and run those scenarios, and comment on the results of scenarios run by others, see those results, and make comments on them, perhaps chat with others all through this. And you know, I'm really, really pleased to discover just in the past year through discussions with Carl Godwin of the HCI Lab, the technologies which can support it. And Stephanie here in the back there is doing the first line of work here, look at this issue of model mapping for causal loop diagrams in a collaborative way. And this is, you know, a first step towards, I think, this grand challenge of getting tools like AnyLogic up there on the web for interactive use, much in the same way you use it at Google Doc with many people at the same time. You can build models in that same way. You can run models. You can interrogate them and discuss them. Okay, I think I'm going to just skip forward here to some opportunities because we're getting into the last 10 minutes of our work. Okay, there's a lot of things I haven't been able to talk about in this class. Model scaling, issues of concurrency, the impact of the language on that. We haven't had a chance to talk about model debugging as much as I'd like. We haven't had a chance to really talk about dimensionality analysis and its use in spotting issues in models and actually simplifying models. But I do want to talk about these tools, about where you might go from here. Suffice it to say, we've taken a look at one package in this class. It's a particularly powerful package. I think it's a more transparent package, but it's far from the only one out there. And you know, in the agent-based context, there's a package called Repass, which is very popular for agent-based modeling, including in a high-performance context, and a package called NetLogo, which is very visual and has some neat components of it for building simpler, smaller models. And then in System Dynamics, there's a whole set of packages that are available, particularly commercially, as well as this package Insight Maker, which is available through the web, although not for collaborative editing. Now, where might you go after this class if you're interested in some aspects of this material? Well, there's a set of classes which I think of as cognate classes. They have relevance to this. Now this says 417. I don't. Is that what the undergrad machine learning class is called this term? Is that, sorry, 498? 820. Yeah, yeah. Because I had heard that it was going to be named 417. Maybe for next year it will. Otherwise, 498. Right? Yeah. And this is machine learning. This course focuses on different types of models. This course focuses, the machine learning course focuses on more statistical models, computational statistical models of phenomena, and as such has a lot of similarity in the sense that you're characterizing data from some underlying process, although you're not actually characterizing the process so much as sort of associations within the data, relationships in the data. 371 and 470 build on many principles that were also articulated within this class. And I'm teaching 470 next term. I'm also teaching 371 next term. Both are classes in the software development area, but they focus on different aspects. 470 is much more focused on certain technical aspects of software engineering. 371 much more so on the medium and large scale group context. Building software for clients in larger groups that demand coordination, demand integration, put a premium on things like continuous integration, on things like peer review and testing, on things like risk management, and where they're delivered in an incremental fashion. The internship program is a great program for many folks. I'm one of the co-directors of that program, and I think very highly of it and the opportunities afforded. So the Computer Science Professional Internship Program, if you're not already familiar with it and you're an undergraduate in your third year, and even if it's in your fourth year and you want to come back, you know, you have more courses to do next year, it may be an option for you, and you might want to check it out. There's some great opportunities there. There are also some modeling opportunities, which I'm trying to get reflected in the CSPIP, the official internship program. But we have partners in across Canada, in the US, and in Australia that are very interested in exchange opportunities with students or having students who have some modeling background come and fill modeling positions. So if you have interest in modeling and interest in overseas travel, there may be some opportunities there. Some are research. We do research in our lab. Kevin Stanley also has folks in areas of overlapped interest, which he supervised. And over the summer, I run boot camps that cover a lot of this material for people from around the world. A fair number of students from these boot camps get hired, either on a long-term basis or on a per project basis as a consultant to help advance projects. Some great opportunities can come for them, opportunities for grad school, opportunities for jobs. And for anyone who's really interested, the Santa Fe Institute has a summer program for undergrads that provides immersion in complex systems methods and aspects of dynamic modeling, foremost among them. Don't have time to go into 470, but I'll put up here on the website some of the topics we'll be covering next term, including things like aspect-oriented programming, reflection, lazy APIs and streams in Java, use of higher order programming, some metalinguistic abstraction, domain-specific languages. Okay, I think that's all I have time for today, and all I have time for, indeed, in this class. So it's with a bit of a heavy heart that I'm going to have to close the class. I'm very pleased that many of you have been working along well with your projects and with your problem sets. The marker remains behind in his marking efforts. I'm very aware of that, and I have been poking him daily in recent times to get you back all of your problem sets, which will be back soon. He is working hard on juggling that with some other obligations, but I'm going to try to get those back to you within the next week from today. Okay, so all the problem sets. We will have at least one review session, and I'm behind in posting the schedule for doodling it, for figuring out when it's going to be scheduled. Part of the reason is my schedule for next week is up. It's been uncertain until tonight. I should finally hear back what my schedule is for next week, and at that point, likely tonight, I will post a doodle poll, and maybe tomorrow. I'll post a doodle poll for times for review session. I will also continue to hold office hours. The exception of this is tomorrow, when I won't be able to hold it, but starting again on Thursday, I will hold office hours, and likely at the end of the day, Friday as well. And then next week, if possible, I will hold office hours as well, including up till just before the final exam. Final exam is on the 19th. I will be with you for the exam, and I will be happy to pass out some sample questions prior to the review session, which you could take a look at and then ask me about. At the review session, I will come with some slides, but I view much of my obligation there, much of my job there is to get quizzed by you, in the sense of you tell me, solve this, do that, answer this question from the sample exam, and I will say, yes ma'am, and I will deliver on that. So a lot of what I'm going to be trying to do there is walk you through solutions to things, tell you how I would answer this or that on the sample questions or for questions that you bring to the final, okay? The final exam will not involve a practical component. It will not be in this lab building models. It will involve some short questions. It will involve some larger questions. It will involve some analytics and some qualitative components as well. So I may ask you to draw causal diagrams. I may ask you to draw a stock and flow. I may ask you to write the equations for stock and flow and solve them for equilibrium. I may ask you to describe how you would, what pieces you might use to build a model that would include such and such components in any logic, etc. That being said, I haven't planned the exam yet. So those are some things on top of my head. Okay? That's all for today. It has been my great privilege, pleasure, and honor to have you in this class. I look forward to further interaction. The best of luck with the closing of this semester, with your final projects, and with your other exams. And I hope to see you in the office hours and then again in the final review. Okay? Thank you very much. Grateful. Thanks. Good to see all of you. Good luck with your exams.